Hello, welcome to the second video with corrected audio of digital continuing education in Blue Valley and geometry. In our last lesson, we introduced the three most basic types of area formulas. We talked about the area of a rectangle/parallelogram, a triangle, and a circle. In this lesson, we're going to start investigating more advanced and involved kinds of quadrilaterals and their area formulas. They end up being related to the triangle and the parallelogram ones we discussed in the last lesson, though, which is really nice. To start off, let's look at the area of a trapezoid. Now, we can read that description in just a second, but let's look at a trapezoid for just a moment. What we'll notice is that a trapezoid really has three components. It has two triangles attached to a third rectangular core. Now, if we wanted to find the area of a trapezoid, it means that if we wanted to, we could find the area of triangle 1, the area of triangle 2, and the area of the quadrilateral in the middle, and add all those together, and that would work just fine. However, there's an even nicer way to tie all these formulas together. And the way that we do that is like this. What we observe is that when we indeed draw this particular height into our diagram, separating the trapezoid, we'll notice that each of the triangles on the side, we've talked about how the area that they enclose is half of the rectangular space that they span. What this also means is that I can then take and I can actually go halfway along the triangle and cut that particular component off. When I cut that off, what happens is that component is actually the exact size to fill the gap beneath the other component, meaning that you'll notice by cutting off the edge of the trapezoid and attaching it to the bottom, I start constructing a rectangle out of its pieces. And if I do that to the same process on the other side, again, I split it in half, cut off that edge, and then attach that edge to the bottom down here, I will actually end up with a perfect rectangle like so. Pretty close. Okay? Now, what does that mean? It means that the area of a trapezoid could be represented as the area of some parallelogram. But how does it relate? Well, notice that when we cut this side, this triangle in half, and this side in half, and attach them, what we were doing is we were averaging the extensions of those bases. Well, how do we find an average? Well, we average things together by adding them and dividing by the number there are, the two wings. In other words, we are going to add together the bases and divide by 2. This gives us that average rectangular shape. And once we have that, we'll multiply that by the height, which doesn't change. So that means the area of a trapezoid can be written like this: half the sum of the bases times the height, or even easier, you can think of it as the average base times the height. So it's really just base times height. What we have to do as a calculation, though, is first figure out what that base would be by averaging the top and bottom. Okay, now that means that we can actually work with a formula. So if somebody said, hey, guess what? I know the area of a trapezoid. Can you find the height? Again, we would just set up our equation and say, well, I know area of a trapezoid is the average base times the height. That's area. And then you'd fill in what you know. Well, let's see what I know. Well, I know the area is 104. I'm asked to find the height, so that's unknown to me. And what about the average base? Well, what's the average of 10 and 14? Well, that's 12. Go to our process here, and we say, well, I have one variable, so I can solve it. I divide by 12, and the height is thus, in this case, 8.6 repeating. That is how many units our height is. And we're done. So again, this formula, average base times height, allows us to find area even of trapezoids as well, which is pretty handy. Okay, now where does this get a little bit more involved? Well, the one place this gets a little bit more involved is when we look at trapezoids that maybe aren't as nice as we would like them to be, where we have to do some calculations before we can move on. And you'll notice that's like this example right here. Here we want to find the area of the trapezoid. But the problem is, while I know the bases, I don't know how tall this trapezoid is. Notice this 13 inches is up the side. Remember, height has to be perpendicular to the base. This 13 inches is not perpendicular to either of those bases, so it is not a direct measure of height. It's a slanted height, just not good. So we need to first find our height before we can find our area. Well, how are we going to do that? Well, what we're going to do is just like we kind of mentioned above with the trapezoid. We're going to find a corner where there's a trapezoidal wing attached. And we're going to drop down a straight line measure of height. What this will do is it'll create for us a right triangle because height is perpendicular to the base. And it will break things up in a very helpful way. Because notice, I know up here that there are 11 inches from this corner to this new corner that I've created, which means at the bottom there's 11 inches from this corner to that corner. So I can start to break up this trapezoid into parts. If the total thing was 16 inches, that means that what's left is 5 inches over here. Now notice, this is a right triangle in which I know one leg is 5, the hypotenuse is 13. So how would I find the new height? Well, I do Pythagorean theorem. When I do Pythagorean theorem, I'll find that the height is 12 inches of both the triangle and the trapezoid. Well, now I want to find the area of my trapezoid, but remember the area is just the average base times the height. What's our average base? Well, the average of 11 and 16 is 13.5. What's my height? Well, my height is 12. Multiply those together. Oh boy, we'll get 162 inches squared, I believe. Somebody can check me if you would like. But we multiply those together and there's our area, just like that. Now, sometimes when we draw in this altitude, this measure of height, it won't make just a normal right triangle. It'll actually make a special one, which means we may not even have to do Pythagorean theorem. Look at this example over here and ignore that. Notice over here, when I do the exact same process, I draw in my measure of height. I notice that I immediately create a 30, 60, 90 triangle. Well, those are great because I can move from the hypotenuse to the short leg by dividing. And the factor of change in a 30, 60, 90 from hypotenuse to short leg is a factor of 2. That means this down here has to be 6 units. Well, if that's 6 units and the whole bottom is 28, that means that the rest of it is 22. Now, I need to know the height of this particular trapezoid to find the area. But again, it's very convenient because to go from my short leg to my long leg, I'm going to multiply. And the factor of change is square root of 3. So my height is 6 square root of 3. Nice. So what's my area? Well, again, we simply write out our formula. The area of a trapezoid is the average base times the height. My average base is the average of 20 and 28, which is 24. And my height is 6 root 3. We multiply those together, and we get 144 square root of 3 units squared. That is my area. And I'm done. So again, what I want you to notice is that area of a trapezoid is just like the area of a quadrilateral, or in particular of a parallelogram. The only difference is we might have to use our special right triangle rules or some of those tools in our toolbox in order to actually find the heights or the bases that are relevant. Now, the last formula we're going to talk about today is the area of a rhombus and a kite. And the nice thing about the area of a rhombus and a kite is that it just so happens that when we draw in the diagonals of a rhombus or a kite, like so, we end up subdividing that rhombus and or that kite into 1, 2, 3, 4 triangles. And we already know that triangles have an area that is half that of the rectangle that encloses them. Well, if we have 4 triangles that are all half of the area that encloses them, we're half the area of the large rectangle that encloses them. What are the dimensions of that rectangle? Well, notice the rectangle is as wide as the first diagonal, and it's as tall as the second diagonal. That means that the formula for the area is half the diagonals multiplied together, because those are the length and the width of the box that surrounds it. So really, your rhombus and your kite are just triangles. It's just a bunch of them at once. And so our shortcut formula allows us to find it without finding each triangle separately. Again, we could use a formula. If someone tells us, hey, I want you to find the area of the kite, given that I know that this diagonal maybe is 6 units and this is 5. Again, we don't have to worry about splitting this up and finding each individual triangle. We can just say the area is half the product of the diagonals. Because again, if we were to put a box around it, that box would be a 5 by 6 box, and our rhombus would take up half of that, which again means our area would be 15 units squared. In this case, it looks like it's centimeters. Great. Now, in the most involved forms of working with rhombuses or kites, we might need to draw in our diagonals in order to find more key information. When we draw in our diagonals, you'll notice this splits this into 20 feet and 20 feet. And we need to find, again, it's a rhombus, so all of these sides on the outside are the same. This is 25 feet, this is 25 feet, this is 25 feet. And the only thing we don't know in this particular juncture is what this length of this part of the diagonal is. And again, we would just simply do Pythagorean theorem in order to find it. And when we do, we would actually discover that this just so happens to be, 15 feet. And this is then 15 feet. So what's the total area of this particular rhombus? Well, again, we're picturing a box. That was a horrible attempt to draw a box that surrounds our rhombus. That was a slightly better attempt. But the box that surrounds it, again, the rhombus is made up of triangles, which are half that area. So the area is half diagonal 1, which is 30. That's the width of our box, times diagonal 2. That's the height of our box. Multiply that all together, and we get that the area is going to be 600 feet squared. So all this to say, these two new quadrilaterals, in this case being the trapezoid and the rhombus kite, those are both related directly back to the area formula for a parallelogram and a triangle. Now, one final note. Notice that with a rhombus is a parallelogram. So as a final note, keep in mind that that means that the rhombus can be found, its area, as either base times height or 1/2 the product of the diagonals. Very much dependent on which one is easier to find in that particular problem. Awesome. Thanks so much for tuning in. I'll see you on video 3.